I'm just gonna go over this for the sake of the video, all right? You guys can just nod or whatever, nod off for a while. All right, the problem on page 8, the class did on whiteboards, so just for those of you who are watching this video, all right? To get the concentration of nitrogen dioxide, we used experiment 1 because the fluorine was held constant. And we looked at what happened to the rate as the concentration changed. All right, and we see that it was first order as the concentration quadrupled, so did the rate. And then we did the same thing for the fluorine. We used experiment 1 and 3 because that is when nitrogen monoxide was held constant. And we looked at what happened to the rate as the concentration was changed, and we found the exact same thing, that the fluorine was also first order. All right, so we add up the orders. 1 plus 1 is 2, so the overall reaction is second order. The rate law then that would put this together is rate is equal to K times the concentration of F times the concentration of NO2. And then how would we determine K? Well, we'd take any of the experimental data and we would plug in the numbers. I used experiment 1 and I plugged in the appropriate numbers. And then we solve for K, making sure that our units cancel correctly. All right, and that is how you would determine the order of reactants, determine the order of reaction, and write the appropriate rate law with calculating the K, all right, with the correct units. And as I said, on most free response, if you can do this, you got 4 out of 5. You're going to get 60 to 70% of it, just like that, if you didn't do another thing on it. Okay, and just to finish out lesson 3, because this can kind of throw you, you can have fractional orders, okay? And let me show you how that would work. If you came to something like this, 2 to the x equals 1.41, all right? Well, 2 to what will get you that? Kind of tricky, you know, it's just really the square root, isn't it? So it would be x, in this case, would be a half. And then those rate constant units get real fun. All right?
Well, with those you can just do logs, right?
Yeah.
That might be too specific, but
Yeah.
you could probably move it somewhere.
Yeah. But I just want you to know that orders can be fractional. All right? I don't think I've really ever seen that show up on the exam, but if it did, it might show up on the multiple choice just as a, here's the rate law, what would be the units? And then I don't want you freaking out about 2 to the half, what the heck is that? And then, all right. Remember then the vocabulary, let's just summarize that again. When we talk about a rate expression, it's just in general terms. It's rate equals something. Okay? Something more specific, a rate equation is when we're using the balanced chemical equation and looking at rate from the disappearing, is that 2 S's?
No.
How do you spell disappearing?
D-I-S-A-P-P-E-A, wait.
E-A-R-I-N-G.
Of reactant or appearing of the product. But we're looking at one thing. A rate law then is putting it all together. A rate law is looking at the interaction of the reactants and experimentally determining the order. All right. So expression, rate equation, rate law. Any questions on that? Okay. There an amazing limitation to rate laws. And let me give you a real life example. Let's say North Korea suddenly decides it doesn't like Murfreesboro, Tennessee. Don't know why. And decides to nuke us. Aha, but we're smart. We have built an incredible bomb shelter. All right? So we're sitting here in this class, and all of a sudden, over the speaker, students proceed to the bomb shelter, incoming nuke from North Korea. And while we're all cursing Kim Jong, whatever his name is, we make it to the bomb shelter, and now we're all sitting in there. And sitting in there. And finally, somebody asked, when do we get to leave? And Oscar says, I'm all over this. We just had kinetics. I know that all nuclear reactions are first order reactions. So I know the rate at which we'll get to stable isotopes and we can go out. The rate is 28 minutes. In 28 minutes, well, no. The concentration is, they're decomposing, getting to a stable isotope at a rate of, whatever molarity per second. Oscar, you've just given us the rate. That wasn't really helpful. So when can we leave the shelter? What time do we have to stay in here until those isotopes decay into something stable?
That sounded pretty advanced, but it doesn't help.
Yeah. All right, so these rate laws aren't all that helpful if we're saying how long does it take to get to a certain concentration. All right? Okay, we have not put in time at all here. The only thing we know is how fast it's going. Once again, the analogy I used with you going on a road trip to St. Louis. If your mom called and said, how you doing? Going 70 miles per hour, have you given her much information? Or 69 miles per hour to make mom feel better. She calls you 2 hours later, how's it going? Going 69 miles per hour. You're not saying, well, we left Nashville at 4, and at this rate, we should get to St. Louis 6 hours. All right, so all that a rate law will give you is the rate at which a reaction is happening. If you want to know how long will it take me to get to a certain concentration, it can't tell you that. It is limited. It is the only thing a rate law can do is give you the rate at which the initial concentration is going to product. That's it. Now, does that mean we can't put time and rate together?
I guess not.
No,
Right.
no.
You ask if it was.
Now, time for a couple new vocabulary words.
That's my favorite.
This is not just a rate law. This is called a differential rate law. So we can call it a rate law, or we can call it a differential rate law, or they can just show, differential rate law. Not to be confused with a URL, right? Anyways, okay. I've been on those stupid videos too long. All right, a differential rate law. Okay, what do you suppose the term is if we want to tie time into it? Integrated rate law. But we'll ignore the calculus involved, except for Cruz, who seems to thrive on it, and then confuse poor Sydney. All right? All right, so what we're going to do is that we're going to well, we're not going to personally integrate the rate law. We're going to see what it looks like after it's been integrated. How's that? We'll just say TAMO, then a miracle occurs, all right? Now, this is lesson 4. And we're going to see that every order reaction integrates differently, of course. All right? And there's key features, properties of a ordered reaction that we're going to look at. We're going to look specifically at 0, 1, and second order reactions. And to keep this simple, when we're looking at integrated rate laws, we're only going to have one reactant. All right? Doesn't mean that's the way it happens, but that's the way it happens for us in our little ideal world here in high school. Okay. You're going to go to college and go to physical chemistry and say, boy, I'm all over this. Oh, good Lord, what'd they do? All right. Okay.
Are the integrated rates specific for each order, just like the units?
Now, there is some information on your reference sheet, and I will actually show you one of these pages where I make you show the modifications so that you can use the information. All right. Okay, so let's look at this. Let's take it from a first order reaction. All right, and let's write a rate law for a first order reaction. And this would be, A goes to B. That's the equation, and this is a rate law for a first order reaction. All right, now, the equation that relates concentration to time, once it's been integrated, and this is on your reference sheet, so you don't have to memorize it, right, is this. The natural log of A at a certain time is equal to negative KT plus the natural log of the concentration, initial concentration of A. So if I want to know, we go to Oscar, when can we leave this bomb shelter? All right. Well, knowing that the initial concentration of the nuclear material, let me call North Korea. Guys, could you tell me how much you put in that nuke? All right. And then I know that when the concentration gets so low, it'll be safe, so I'm going to put that in there, and then I'm going to solve for how long it'll take to get there. Okay? We just happen to know the K of this as well. We're a bunch of magnet school kids, right? In a bomb shelter, we'll figure it out. All right. Okay, now, one thing I want to show you is how similar this looks to the equation of the line. Y equals mx plus b. So is there a linear relationship here? You bet. And will its linear relationship look different than second order and zero order reactions? You bet. All right? Okay, so what does that tell you about the slope? It's going to be negative, okay? It's going to go down, all right? And the graphical linear relationship between a first order reaction is we'll have time on the x-axis, the natural log of A at a given time, and my graph will look like this. All right? Now what that will also tell me is what will the slope of this line give me? K, very good, all right? All right, so if we run an experiment, we can graphically determine the rate constant. Now, will we do that? No, all right? But I do want you to understand what information the equation of the line gives you. In this case, it gives us the rate constant because x is time, y is the natural log of the concentration at that time, and m is the rate constant, how they are related. All right, now this is on the free response. If this is a first order reaction, what would we be comparing? All right, and this is where you'd have to say natural log of A. But a first order reaction is the only one that does natural log. So I mean, this is a unique graph of a first order reaction. It graphs natural log of concentration versus time. It's a negative slope. This is the mathematical equation that you use. All right? So right there is what you need. Now, the math on it is just plug and chug. Given values, put them into this equation and solve for it. Just being careful with units and sign. All right? So let's look. Let's look now at the middle of page 9. It says the decomposition of cyclopropane into propene. Not that that really. So this is what it looked like, just in case you're curious. That's cyclopropane, all right? Now, would these be isomers?
Yes.
Yes, why? Same molecular formula, different structural formula, all right? Okay, so this is the reaction we're looking at. It says it has a K of 6.7 times 10 to the negative fourth S to the negative 1. All right, they didn't even have to tell us it was first order because from those units we would know it's first order, correct? All right, if the initial concentration is 0.25 molar, what is the concentration after 8.8 minutes? All right. Okay, well, they gave us the K is equal to 6.7 times 10 to the negative fourth. All right, but what units in our equation are T in our equation?
Seconds.
Seconds. So what do we have to do with this value? Yeah, convert it to seconds, don't we? All right, now we just simply take those numbers and fill it into our equation. All right, so the natural log of this is equal to negative 6.7 times 10 to the negative fourth times 528 seconds plus the natural log of 0.25. Now that looks horrible, all right? But this, when we take the natural log of 0.25 and add it to this, we get negative 1.74. All right, how do we undo a natural log? Well, we hit second function ln, which is that e to the whatever. All right, so you would put second function ln negative 1.74, hit enter, and you get 0.176 molar at 8.8 minutes. Now you don't have to put 8, but remember to get your concentration right, and remember that your sig figs need to be correct. Okay, so the math of integrated rate laws are easy. What's hard is remembering how they graph and what they graph against. And a couple other things we'll bring up. Actually, there's a whole lot. Just each gets progressively worse. And on top of it, we have a lecture for an hour and a half, you know. All right. But next week we have a lab.
I'm guessing that's on block day.
Yes. If we have a block day.
Yeah, that is
Okay, how long in minutes it take for the concentration of cyclopropane to decrease from that initial amount to 0.15? Well, this time our equation will be the natural log of 0.15 equals negative 6.7 times 10 to the negative 4th seconds to negative 1 times the time times and half the time. Right. The natural log of 0.15 is negative 1.90. This is negative 6.7 times 10 to the negative 4th x plus 1.39, which is the natural log of that. All right. X finally ends up being 761 seconds, but what did the question ask for?
Minutes.
Yeah, because they do that on purpose to make sure you know what those units mean. And so we divide that by 60 and we get 12.7 minutes. All right, so that's how long it's going to take me to get from this to that. Now remember, a differential rate law couldn't have told us that. So we get to do some wonderful complex calculus to integrate it. Now, if you know how to integrate this, then you won't have to do any memorization. All right, but if you're a mere mortal, then you're probably going to have to. All right, C is interesting because when we look at percentages with a first order reaction, something amazing happens. That doesn't happen with the other ones. All right, how long in minutes will it take to convert 74% of the starting material? Okay, what you're calculating is what's left. Always remember that. So if 74% is converted, what's left? 26%. All right, so let's look at this. If the initial amount is X, then the amount at time, a certain time, will be 0.26X. That makes sense? Now, you don't have to know how to do the math. I'm going to show you this so you'll see what the end result is. All right? Because this is cool and this is unique to first order reactions. All right, so we're going to say the natural log of 0.26x is equal to negative 6.7 times 10 to the negative 4th times time plus the natural log of x. All right? So the natural log of 0.26x minus the natural log of x equals negative 6.7 times 10 to the negative 4th times time, right? Well, an interesting math fact about subtracting natural logs, do you know? You divide them, yeah, very good. Okay, so we can say that the natural log of 0.26x over x, what happens? So in first order reactions, percentages will always be the natural log of the given percentage over the K. And that is unique to a first order reaction, and it's unique because this always happens mathematically. You don't have to know this, okay? You just have to know that in first order reactions, the percentage, and guess what that means? That it's independent of the concentration you start with. So, first order reactions is that first order reactions have consistent half-lives. Well, let's get to that. First order reactions, let's stop. We'll get to, we haven't gotten half-lives yet, so I don't want to move ahead. All right, but you can see that any fraction will be the percentage over t, so the implications are what is a half-life when you're 50% through it, right? Okay, so the half-life of a first order reaction is consistent and not dependent on the initial concentration. That's nuclear reactions, isn't it? They have consistent half-lives, don't they? And the initial concentration always goes down half by that time. Doesn't matter what the initial concentration is it? Kind of cool. We didn't think of that back when we were doing half-lives. But no other order reaction will have this, all right? That will have consistent half-lives that are independent of the initial amount, because it cancels mathematically. And it's always the percentage over the K. Now, back in the day, when they had, way back in the day, you know, they used to have stuff like this on multiple choice when you could use your calculator on multiple choice. And you didn't get to use your reference sheets, you just had to remember that. Now, of course, you guys are all idiots, so they give you the reference sheet and take the math out of it. Not you personally, they're just saying collectively you can't handle it, so you should be insulted. No, you're going, yes, that's me, I can't handle it, yeah. Okay, now, so let's turn page 10 then in our lecture notes. And we'll finish this off in lesson 4, and the only thing we'll have is lesson 5 on Monday. All right, and we'll be done because I videotaped 6, 7, and 8. All right. Let's say you're just given some data, and you want to say, what order is it? All right. Well, I know that if I take the natural log of the partial pressures and they graph, and I get this, I've got a first order reaction, right? So what I would do is I'd go through and I'd say, okay, what is the natural log of 284? It's 5.64. The natural log of 220 is 5.40. Natural log of 193 is 5.26, and you get the idea. All right, so if I take the natural log, and when I plug that into graph my data in your calculator, or you actually do it the good old-fashioned way, and we do get a linear relationship that is negative, it's a first-order reaction. Now, if we get something like that, it's not a first-order reaction. Or if we get something that's this, it's not a first-order reaction. Okay? So we can take any data and first try the natural log and then see if it graphs. And if it does, it's first order. So we can graphically determine if a set of data is first order reaction. All right. And then finally, what I just alluded to is they will discuss half-lives, but fortunately they're only going to do half-lives probably with first-order reactions because of this phenomenon, but it is unique to a first-order reaction. You know, half-life. Half-life is going to be, and this is what they have, my 0.697 over. This is what they have on your reference sheet. And you say, for heaven's sakes, what is 0.697? Well, it's the natural log of 0.5. That's it. Okay, they've just done the work for you. Okay, so half-lives of first-order reactions are consistent, and they are independent, not dependent. And that is unique to first-order reactions. Okay, so the integrated rate law, how it graphs. It's information about the half-life, and the units of K are what you need to know about a first-order reaction. All right, we'll stop there. Monday, we'll look at second-order and zero-order reactions and put them together. And we will be done lecturing on kinetics.